Hello, class. So we are now in section 2.7, which this is actually the last section in chapter 2. All right, and we're going to talk about one-to-one functions and inverses. All right. And this is pretty related to that composition section we just did a little bit ago, but I want to start off with talking about f of x squared, right? And so I'm going to plug in two numbers, -2, right? That's 4, right? Because -2 squared is 4. And then I'm going to plug in 2, and that's 4, right? And they're both 4, and that's fine, right? It's a parabola, and here are the 2 points, right? It makes total sense, okay? So now I want to kind of recall, all right, functions, right? So if we remember, if we have a domain and a range, and if we're sending a number to two different places, like here, right? This is not a function, right? This is a relation. Okay. Because you're one input, two outputs, right? This is bad. So then we're like, okay, a function is something that sends one number to specifically one number. Okay. So here, right, this is like x squared, sort of, right? So this is okay. This is a function. But it's not one-to-one. Okay, so being one-to-one is being like a special kind of function. All right. So one-to-one specifically, all right, is that you send each element in the domain to one specific element in the range. All right, so here's like the math way to say that. So one-to-one, functions are functions such that, okay, here's one way to define it. So if you have different inputs, okay, so if you have an x1 and an x2, then you have different outputs. So that means f of x1 cannot equal f of x2, okay? Now, so that's one way to say it, and then here's the other way to say it, and I think most people like using this way more. So this says if you have the same output, okay, then your input needs to have also been the same, okay? All right. So I'm going to kind of go overboard here with this example, but I'm going to prove, and this is like an important word, okay, in math. I'm going to prove that 3x plus 5, okay, this line, I'm going to prove that it's one-to-one, okay? So I'm going to assume that f of a equals f of b. So instead of like x1 and x2, I'm just going to use a and b, okay? So I'm going to assume this, and then I'm just going to see what happens. So then I plug in the a, right? And I plug in the b. Then I'm going to subtract 5 to both sides. So you get 3a, 3b. Then I'm going to divide 3 on both sides. And you get a equals b. Ta-da! Right, so I started here, and I ended up here, which that is like the definition, right? I started here, then this. So thus, f of x is 1-to-1. Okay. Now, like there might be like one homework assignment that has you do this, but that's not really a big deal. Proving stuff is a little fancy for us. Disproving stuff though, that's not that hard. Okay, so here I have a function. All right, 2x squared plus 1. Okay, I want to disprove it's 1-to-1. So how do I do that? Well, to disprove something is 1-to-1, you just need a counter example. So you can just show me two points that get mapped to the same place, and then it'll be good. So for example, I can plug in 1. That gets me 3, right? Then I can plug in -1, which is a different point. But then if I do the work, right, you see that it's also 3. So that means, right, if I drew the little picture over here, that means -1 and 1 both get sent to 3, which is bad, right? That means it's not 1-to-1. Okay, so to disprove something is 1-to-1, you just literally need to find two numbers that get mapped to the same spot. And like 99% of the time, that'll work just by plugging in the plus version and the minus version. Okay, so like +1 -1 +2 -2. Okay, so that's 1-to-1. Now I'm going to show you how to do it if you're not given the function, if you're just given the picture. Okay, so if you're given a picture and you want to know if a function is 1-to-1, you need to do the horizontal line test. Okay, so the horizontal line test is extremely similar to the vertical line test. Okay, so here I have x squared, and what you do for the horizontal line test is you draw horizontal lines. Okay, and we see here that the function crosses the horizontal line more than once, right? So this fails. Horizontal line tests. Okay. Now an example of a function that passes horizontal line test is this one, x cubed. Okay. No matter where I draw the horizontal line, okay, right? It doesn't matter where I draw it. It's always only gonna cross once. So this passes the horizontal line test. So x cubed is 1-to-1. Passes H test. Okay. But the horizontal line test, right, just like the vertical line test, you can have like a whole bunch of special cases. So here, I'm going to draw the function x cubed minus x, okay? And it looks like this, okay? So if I do horizontal line test, right, with all of the lines I just drew, then I'm fine, okay? But specifically, if I go like here, right, I'm not fine, right? I crossed 3 times actually. So this also fails horizontal line test. Okay, and is not 1-to-1. Okay, so it's not like an even and odd thing. Okay, it's actually a little more complicated than being even and odd, because this function is odd, but it still fails horizontal line test, so it's not 1-to-1. Okay. All right, but H test, I hope it's pretty easy. Don't get it confused with vertical line test. Okay, this is to check for 1-to-1, not if it's a function, right? Vertical line test is to check if it's a function, right? All of these would pass vertical line test because they all are functions, okay? But only some of these pass horizontal line test because they're not 1-to-1, okay? Okay, so why am I talking about 1-to-1 functions? Really, it's because we want to talk about inverses. okay, or when are functions invertible? Okay. Just to kind of spill the beans, just to get to the point. A function, okay, is if a function is 1-to-1, all right, then it's invertible, or then it has an inverse. Okay, so that's why we care about being 1-to-1, because if you have it an inverse, you are 1-to-1, okay? And that means if you aren't 1-to-1, then you don't have an inverse, all right? So an inverse is the control Z of the math world, okay? So let's pretend I have a function. Okay, it goes 1, 2, 3, and it goes like, I don't know, 5, 10, 15. Okay, and we know that a function is a rule, right? So this is what my function does. Okay, then the inverse function, which we write like this, okay, just does the opposite thing. Okay, so the red is the inverse function. All right, so if f of x equals y, then f inverse of y equals x. Okay, it just literally sends it back. Okay, now big deal. Okay, this -1 here is not a power. Okay, very important that you do not get this confused with a power. Okay, it's not a power. This is not like 1 over f of x. Okay, it's just notation. Okay, it is not a like -1 power. Right? Okay, so if an inverse just does the opposite thing, then that means you should be able to tell me what happens with this. Okay, so if I have a function, I'm not going to tell you what it is. Okay, I'm just going to tell you this info. That when you plug in 1, you get 2. When you plug in 3, you get 5. And when you plug in -2, you get 7. Okay, so we know that these are like points, right? So 3, 5, -2, 7. And so to do the inverse function, we could just kind of flip them. Okay, so what I mean is, then you can tell me that f inverse of 2 is 1. And f inverse of 5 is 3. And f inverse of 7 equals -2. Okay, so it just does the opposite, right? F takes 1, sends it to 2. F inverse takes 2, sends it back to 1. Okay, hopefully not too difficult. Okay, and then so here is a property of an inverse. Okay, so this is how we can test if functions are inverses. All right, properties of inverse. So if you compose them, so if you do f inverse of f, that should be, right, f inverse of f of x. It should perfectly cancel to x. Okay. But here I'm in the domain of f of x. Okay. And then if I do it backwards, right, so f of f inverse, that also should cancel to x, except now I'm technically in the range of f of x. So the domain does weird stuff, but let's ignore it. Okay, so an example of a question you could get is check that cube root of x and x cubed are inverses. Okay, so how do we check if they're inverses? Well, just call one, call this f, call this g, and then you can just figure out what's fog and what's goff. So f of g is cube root x cubed, which cancels to be x, and g of f of x is cube root of x cubed, which is x. Okay, so they both cancel to x, so that means that they are inverses. Okay, and then here's the famous example of like the trick question I showed you guys last time. Square root of x and x squared, right? These are not really inverses of each other. Okay, because when you do this, this is absolute value x. And when you do it the other way around, square root x squared, this is x. Okay? So as we can see, they both don't cancel to x. It almost works. This is like almost an inverse, but not really. Okay. All right, so you can use this to test if stuff is inverses, right? If you want to test if two things are inverses, you just compose them and see if they cancel out, okay? But a more popular question, all right, is finding an inverse function. So I give you a function and you tell me its inverse. Okay, now this I guarantee is on the test, okay? Very specifically, a specific style of this question is on the test too. Okay, but finding an inverse. So, your book likes to kind of make this like a process. Okay, so let's do this process together. So, example. Okay, I want to find the inverse of this line, 2x plus 3. Okay. So step 1 will be replace f of x with y. Okay, so step 1, y equals 2x plus 3. Okay, step 1, not hard. Okay, step 2 is you swap all x's and y's. So wherever you see a y, put an x, and whenever you see an x, put a y. So x equals 2y plus 3. Okay? Now, step 3, this is the most important, this is the hardest one. Okay, is you got to resolve for y. So I'm going to subtract a 3 to both sides, get x minus 3 equals 2y. Then I'm going to divide both sides by 2. So y equals 1/2 x minus 3 over 2. And that's a line, okay? And then the last step, step 4, replace y with f inverse x, because that is the answer. F inverse equals 1/2 x minus 3 over 2. Okay, so that is how you find an inverse. Okay, and I can prove it works. Okay, so just just to check. All right, let's see. Okay, so if I do f of f inverse, so that's going to be 2. And then I'm going to rewrite this. I'm going to stick them together. So like this, plus 3. So the 2's cancel. X minus 3 plus 3. The 3's cancel. And ta-da, you get x. Okay. And then if I do it the other direction, because you got to check both, what does that look like? So 1/2 2x plus 3 minus 3 over 2. Now I'm going to distribute. So you're going to get x plus 3 over 2 minus 3 over 2. Those cancel. and x. So ta-da, they both cancel. So they are inverses, okay? All right, now, this is the question that I'm guaranteeing is on your test. All right, not this exact one, but rational functions. All right, I really like forcing people to find the inverse of rational functions because I think it's like a really good test of algebra. Okay, can you move stuff around fluently? Okay, so find the inverse. So step one, replace f with y. Step two, swap x's and y's. So right here I have two x's, so that means I'm going to have two y's here. Okay, and then step three, this is like the main part, is I have to solve for y again. So I'm going to multiply both sides by the denominator and get 2y minus 1 equals y plus 3. I'm going to distribute 2xy minus x equals y plus 3. And here's where most people get stuck because they don't really have like the goal in mind, right? The goal is to solve for y. So if you're going to do that, you should probably get all of the things with y on one side and all of the things without y on the other side. So I'm going to move the x over and the y over. So 2xy minus y equals x plus 3. Now here, I'm going to put these parentheses here because I'm going to magically factor out the y from both sides. Okay, so if I do that, I'm going to get y 2x minus 1 equals x plus 3. And then I'm basically done because the answer is x plus 3 over 2x minus 1. Okay. And then the inverse equals x plus 3, 2x minus 1. Did I accidentally? I 100% accidentally made this function its own inverse, which is pretty interesting. That's funny. I'm amused. Okay. So that's possible. First of all, let me tell you that like it's totally possible. Let me do one check. Let me do half the check. So I'm gonna plug. Well, actually, this is just the check because it's the same. So f inverse of x. So plug it into itself. So x plus 3 divided by 2x minus 1 plus 3 over 2 x plus 3 2x minus 1 minus 1. Okay, so this is a little not pretty. Okay, I'm going to multiply the top and the bottom by 2x minus 1. So you're going to get x plus 3 plus 3 2x minus 1. And then 2x plus 6 minus 2x plus 1. So I'm distributing. So the 2x's cancel, and I'm going to get a 7 on the bottom. And then the top, what happens with the top? So I'm going to get 6x minus 3. Oh, and the magic is happening. Right. The 3's cancel, and the 6 and the 1 add, so 7x over 7 cancel. Ta-da! It works. Okay, so this function really is its own inverse, which this is interesting. Right, I'm interested in this function. All right, but yeah, there we go. All right, it is its own inverse. Very amusing. All right, let's do another one. Okay, because I said this literally is guaranteed to be on the test. Okay, so f of x equals 2x minus 3, 3x plus 5. Okay, so hopefully this one isn't its own inverse. No promises, because I just made it up. It's 3x plus 5, okay. So swap, so 2y minus 3y plus 5. Move it over, so 3xy plus 5x equals 2y minus 3. The y and the x's, so 3xy minus 2y equals negative 5x minus 3. Factor, so let me move this over here. Y, 3x minus 2 equals negative 5x minus 3. And then you get the answer, which is negative 5x minus 3 all over 3x minus 2. Okay. Which, yeah, okay, it's different. It's not literally the same. It looks a little similar, but it's not, it's different. Okay, so this is the inverse. Ta-da! All right. Okay, so I encourage you to study these. Okay, just make a rational function. Its inverse. Now I'm gonna get into a slightly more fancier topic. Okay, so this is not that important. Okay, but I'm gonna talk about domain restrictions. Okay, so this is where you take a function, maybe like x squared, right? And we remember that x squared is not 1-to-1. Okay, but right, what if I took x squared, right, and I look at its graph, right? Its graph is like this thing, right? What if I just deleted this left chunk? Okay, what if I just, it's this? So that question is, what if I restrict its domain to this new one? Okay, so this is why it's called a domain restriction, because I'm literally like slicing off some of the domain. Okay, now it is 1-to-1 though, right? Because now it will pass horizontal line test, because like the left half is gone. Okay, so in fact, right now you can do y equals x squared, and then x equals y squared, square root both sides, y equals square root x. Ta-da! So that's the inverse function. But okay, realize that, like, what if I restricted the domain differently? What if I chose to keep the left chunk and not the right chunk? So if I have this new domain, it's still 1-to-1, but when I do this, right, and I flip them, x, y squared, now when I square root both sides, oh, I didn't. Okay, I think we're stuck on red for the rest of class. But y is going to equal negative square root x, okay? Because I only have negative numbers. Okay. So that's just like a fancy thing. Okay. And then now really the kind of most useless part is graphing these. Okay. So if I have x squared, it looks like this, then its inverse, right, is the square root of x, which looks like this. And so if I draw this purple line, which is actually a red line, excuse me, we can see that they are symmetric across this red line, right? And so that is a special thing about inverses, okay? Is that you're literally flipping them across the identity function. So another good example, if you remember when I taught you the original functions, right? I told you that x cubed and cube root x, right? They literally look like they're sideways of each other. That's not an accident because they literally are, because they are inverses of each other, okay? And I don't have decimals pulled up or else I would show you, but you can just believe me. All right. And then lastly, this may show up on your test, okay? Definitely not like a final, but if I have a function, okay, like 2x plus 3, 3x minus 5, right? And I find the inverse. So 5x plus 3, 3x minus 2, okay? If we look at the domain in range of these functions, you'll notice something. All right, so the domain of f, right, is not 3 over 5. Okay. Now, if we find the range of this function, okay, which we could if we graphed it, okay, but it's going to be not 2/3. Okay, but now if I look at the inverse function, if we look at the domain of the inverse, it's not 2 over 3. Okay, my bad. Yeah, 2 over 3. 2 over 3. And if we look at the range of the inverse function, it's not 5 over 3. And hopefully you noticed something, right? Like you noticed that, oh look, the domain of the original function is the range of the inverse. And the range of the original function is the domain of the inverse. And that makes sense because if you look back at like the bubble chart, right, f inverse's domain is this thing, which is the range of f, right? And the range of f inverse is this bubble, which is the domain of the original. So it's literally just flipped, right? They just swap with each other. Okay, so this is a really useful way to find the other one's info, right? Like range, this thing's range is a little complicated to find, right? You pretty much would have to draw it to find the horizontal asymptote. But actually, we wouldn't have to do that because we could just cheat and we could easily see this thing's domain, which we know would be the same thing as this thing's range, okay? So that's one way to find range and domain using another function. It's inverse, okay? But this is really, really a fancy topic, okay? So not something to super stress about if you don't get it. But you know, it is a thing that is useful. All right. But that's it for section 2.7, which actually that means this is it for chapter 2. Okay, so chapter 2 is done. I would say for sure finding inverses, especially of rational things. Okay, this is definitely what you'd want to study from this section. All right, but that's it for today, guys. All right, see you guys next class.